Good morning, students. Today let us continue with the properties of a magnet and magnetic field and magnetic field line. In the last session we have discussed some of the properties of magnet. Okay. Now we will discuss what is a magnetic field line. See, this is how we have just drawn the magnetic field line with the help of a compass. This is magnetic compass and this is bar magnet. And various positions of compass. Compass which is having a small needle inside, right? Now, if you trace that, you will get a field line. What does a field line means? So first of all, we should know what is a magnetic field. Magnetic field is the space around the magnet, the area around the magnet in which the another magnet experiences a force. So magnetic field is the space around the magnet in which a piece of iron gets attracted. It's the area of influence. You can say it's the space of influence of the magnet in which another piece of magnet experiences a force. So if north pole is facing the south pole, it gets attracted. If south pole is facing the north pole, of course it gets attracted. If north and north poles are facing each other, they get repelled each other. So north to north repel each other, north to south attract each other. So it means what? The unlike poles means north south, south north. The unlike poles attract each other and like poles repel each other. So this is the very important property of magnets. So like poles repel each other, unlike poles attract each other. So with the help of that property, we are now drawing what is the magnetic field line. First, let us define what is a magnetic field. Magnetic field is the space around the magnet, or you can say space of influence. Space of influence around a magnet in which a small magnet kept in it, a small magnet kept in it experiences a force. Force is attractive when it is unlike poles. The force is repulsive when it is like poles. When like poles are facing each other, they experience repulsive force. When unlike poles are facing each other, they experience attractive force. Okay. So actually, magnetic field, as I have written, it is roughly I have defined the space of influence around a magnet in which a small magnet experiences a force. But actually, magnetic field is a vector quantity. Magnetic field has magnitude as well as direction also. It has magnitude as well as direction. Now the question comes, how to find out the direction of a magnetic field. So that's what we are doing now, finding the direction of magnetic field with the help of a compass needle. That's what we have done, right? Now, if you look at this, if you again change the position of this very close to the north pole, you will get another line like this, emerging from north and entering into south pole. Similarly, if you draw from here, you will find a line emerging from north, entering at south. So, if it is kept very straight, you will find the line going straight, and here line entering straight. So, you see around the ends in these areas of influence, if you observe, the field lines are very close. The field lines are very close. And what does the direction indicate? What do these directions indicate? These are the directions of magnetic field. These are the directions of magnetic field. So, the magnetic field direction is not fixed. You see, when you are going in this direction, the magnetic field goes on changing its direction in this curved path. So, these magnetic field lines actually gives you an idea of magnetic field direction of the magnetic field at that particular point. Direction of the magnetic field at that particular point. So, you can see here they are emerging from north, entering into south. So, magnetic field has a magnitude as well as direction. The direction of magnetic field can be traced with the help of field line. Then the question arises, what is a field line? What is a field line? So we define what is magnetic field line. Magnetic field line is a line or a curve in which a compass needle kept at that point shows the deflection. It is the direction of deflection of compass needle. Compass needle is a small magnet. It experiences a force of attraction. South pole is attracted towards the north and north pole is attracted towards the south. That's what we have seen here. South pole is attracted towards the north, north pole is repelled away. So north pole is attracted towards the south. So in what direction it is deflecting? When you trace that direction of deflection, we get a magnetic field line. So we define the field line is a curve. It is a line or a curve in which a compass needle gets deflected and the tangent, whatever point you see, for example, if this is the point where you want to find out the magnetic field, you draw a tangent here. The tangent drawn at any point gives you direction of magnetic field at that point. So tangent drawn at any point gives you direction of magnetic field. So tangent drawn here gives you direction of magnetic field. So like this, we can draw the direction of magnetic field. At any point, if you draw the tangent, you see, it gives you direction of magnetic field. So the line or a curve in which the compass needle gets deflected and the tangent drawn at any point on such curve gives the direction of magnetic field. Now, when you look at the diagram, you will find more and more crowding of field lines. You can draw any number of field lines. Any number of field lines. They are all emerging from north and entering at south. These are the properties of magnetic field lines. So I will write second property. This is first property. What is the field line? Second property I am writing. The magnetic field lines emerge from north pole and merge means enter. Merge means enter. They enter at south pole. So always a magnet has a polarity, north and south. I told you what is north pole. When you suspend a bar magnet or any magnet freely, if a magnet is suspended freely, it always aligns along north-south direction. So the north pointing pole is called north pole, south pointing pole is called south pole. So that is the polarity of a magnet. So we have written the property of a magnetic field line. It's a line or a curve. The tangent drawn at any point on the line or a curve gives you direction of magnetic field at that point. And field lines, they emerge from north pole and enter at south pole. And if you actually draw inside, they are going to form closed curves. This is what you are going to learn from the study of solenoids, right? They are going to form the closed curves. Right? See here. Inside the magnet it is reverse. They are entering into south and coming out of north. They are from south to north inside the magnet. Outside the magnet they are from north to south. This is the property of magnetic field lines. These field lines form closed loops. They are going to form the closed loops. They are going to form the closed loops. These are the properties of magnetic field lines. Now, next we are going to learn with this knowledge of magnetic field lines. We are going to learn the magnetic field due to a current carrying conductor. Magnetic field due to a current carrying conductor. Now let us learn magnetic field due to a current carrying conductor. This is a simple circuit. Now this is a copper wire, thick copper wire. You can see a thick copper wire which is taken along the north-south direction, and this is connected with the connecting wires, and here is the plug key. When you close this key connected to the battery, suddenly you will find the current flowing through this from positive terminal to the negative terminal in this direction. Now the copper wire that is taken, thick copper wire, is along north direction, south to north, and the direction of the current is also in the south to north direction. Now when you place compass needle just below that conductor, when you just below this conductor you place this compass needle, you will find the deflection of the compass needle towards west. Towards west. Compass needle gets deflected in the west direction. So when the current flows from south to north, the needle deflects towards west. So this is how we can remember in simple manner. Snow. Snow means what? When the current flows from south to north. When the current flows from south to north, the compass deflects. The compass deflects towards west. It is also called as swimmer rule. Suppose you are swimming in the direction of south to north. In what direction your left hand goes? The left hand naturally goes towards west. So the left hand direction of a swimmer swimming from south to north gives you direction of deflection. So that gives you direction of magnetic field just below the copper wire. Right? Now when you change the polarity, what happens? When you change the polarity, you see this is another circuit diagram. Same thing with change the polarity. Battery, here it is positive in this case, here it is made positive this side. So when polarity is changed, the moment you close the circuit using the plug key, here it is plug key. The moment you close the key, what happens? The current flows in the opposite direction. When the current flows in the opposite direction, look at this. The current through the copper wire, thick copper wire, is now from north to south. It is now from north to south. Very interestingly, the deflection of the compass needle is towards east. It is towards east. So when the current flows from north to south, the deflection is towards east. When the current flows from north to south, in the reverse direction, as you are observing here, when the current flows from north to south, the compass deflects towards east. So how to find out this? Snow rule we can understand. Okay. When the current is from south to north, the compass deflects towards west. Easy to understand. Here it is just the reverse. Here it is towards east. Okay, fine. But there should be some guiding line. What is that guiding line? To understand that, let us consider one simple activity. Suppose we are taking a thick card sheet, and through this thick card sheet we are piercing a thick copper wire, right? And this is connected to a battery with the help of a key, and then to this key these are the connecting wires which are connected. This is the plug key, and on this we are keeping the compass needle. Okay. So this is a thick copper wire. You can call it as AB, a thick copper wire. When you close the circuit, the current flows from positive terminal to the negative terminal in this sense of direction. The moment you close the key, you will find the flow of current from A to B. Now suppose you are keeping a compass needle, and before closing the key, what is the direction of needle? It will be somewhere in any direction. There is no restriction on the compass needle. The moment you close the key, what happens? Interestingly, you will find the deflection in this needle. The current flows from positive terminal of the battery like this, in this way. So it moves from A to B in the upward direction. Suddenly you will find deflection of the compass in this direction. So when you just replace it will be reflecting like this. When you just keep it this side, it will be deflecting like this. So if you go on changing the position, you will find the change in the direction of the compass needle. So you will find that there is a closed circular loop. You will find a closed circular loop. So if I just represent this with the help of a closed circular loop, interestingly, you are getting a circular magnetic field line. You are getting a circular magnetic field line, which can be drawn like this. So this is in one position, according to the reflected direction of compass needle. Again, in this way, if you observe, this will be observed like this. So this is in one particular direction. So how to find out the direction in this case? Here we make use of, to find the direction of magnetic field, we make use of right hand grip rule or right hand thumb rule. We make use of right hand thumb rule. See here, if this is, you have to take the right hand and, okay, I will take the pen. The pen will be easy to understand. Suppose this is the pen in which represents the direction of current. This is the direction of current. I am holding the pen along the direction of thumb. You can see the direction in which the fingers of the right hand, the direction in which the fingers of the right hand curls, that gives you direction of magnetic field. In case the current is reversed, if you change the polarity, then this negative and this one positive. If you reverse the direction of current, the current flows down. When the current flows down, you see the thumb is pointing downwards. When the thumb points downwards, the curling of the fingers is reversed now. It will be in the clockwise sense. Here, when the thumb is upward, it will be in the anti-clockwise sense. So curling of the fingers represents the direction of magnetic field lines. So we follow here right hand rule, right hand thumb rule. You can say right hand thumb rule, right hand thumb rule. To find the direction of magnetic field, direction of magnetic field. So when the current is upwards, see, thumb is upward. When the thumb is upward, the curling of the fingers, you see, they go inwards, they enter inside the board and come out of the board. This is how. When you change the polarity, thumb goes down, the curling of the fingers will be in the reverse direction. So when the current goes down, the fingers are clockwise. So the direction of magnetic field lines are also clockwise. And the current is downwards. When the current is upwards, the field lines are in the anti-clockwise direction. So that gives you direction of magnetic field. So these experiments show that the current carrying conductor, this is a straight conductor. What is this? AB is a straight conductor. So this straight current carrying conductor behaves like a magnet. So this shows that the straight current carrying conductor behaves like a magnet, and the magnetic field lines around the current carrying conductor can be found out with the help of right hand thumb rule. To find the direction of magnetic field. So in the next session we will learn about the magnetic field due to current passing through circular loop. Magnetic field due to current passing through circular loop. Okay. Thank you. Have a nice day.